Okay, do you remember e to the x and sine x? And I want us to go through sigma notation and a first few terms. And I will say, as I say too many times, because we are losing a half hour every single day, and now for the unique thing of today, I'm going to have to move faster instead of giving you time to think. So let's remember that e to the x has the formula x to the n over n factorial. And the first few terms, e to the x begins with 1, and then x, and then x squared over 2 factorial, and then x cubed over 3 factorial, and so on. And I should put a squiggle equal if I'm not having an infinite degree polynomial. Sine, you remember that was an odd degree function. So all of its, if it is centered at 0, as the Maclaurin series is, then it has only odd degree terms in its polynomial. And it does the alternating thing, so -1 to the n. And my odd numbers are created by making even numbers and then adding 1. And I have the same factorial in the denominator as I have the exponent. And then you want to remember what are the first few terms of sine x. And they are starting with x and then alternating to a negative, and it goes up to the next odd exponent, alternating back to positive, next odd exponent, alternating back to negative, next odd number, and so on. Now, instead of going through the entire Maclaurin process of let's take a whole bunch of derivatives of cosine and then find its values at 0, we're going to take a shortcut. And that shortcut is, you happen to know something very special. You know that the derivative of sine is dun, 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 cosine. So, can we take derivatives of polynomials? Yes, we can. I'm going to start with the first few terms. Derivative of x, 1. Minus, I have a constant multiple of 3 factorial in the denominator. And then I take the derivative of x cubed using the power rule, and I get 3x squared. And we'll look at the simplification in a moment. Plus, divided by 5 factorial is a constant multiple. And then derivative of x to the 5th is 5x to the 4th. And again, constant multiple, derivative of x to the 7th is 7x to the 6th. And now simplify. And what do we get when we simplify? And just to make sure you are clear, 3 factorial is 3 times 2 times 1. 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial, and so on. So I also want to look at the sigma form. Yep. So cosine has all of the even terms that e to the x has, and also does the alternating series. And I want to make sure that you recall that 1 is the same thing as x to the 0 power divided by 0 factorial. And even 0 is an even number. So cosine has the e to the x terms for when n is 0, 2, 4, 6, and so on. Sine has it for when n is 1, 3, 5, 7, 9, and so on. And both of them begin with a positive and alternate positive, negative, positive, negative. So it's not too bad to have to remember. And I want to make sure that you see the sigma notation. And I want to take the derivative with the sigma notation to prep you a little bit with what's coming next week. I'm taking this formula right here, and that's my focus. And I want you to see through the individual terms that the negative 1 to the n over 2n plus 1 factorial. As I plug in different values of n, that piece of the formula becomes a constant multiple, which just sticks around. Then when I take the derivative of the piece that actually has the variable x, I use the power rule. And with the power rule, I get drop the exponent and then subtract 1 from the exponent. And then my factorial in the denominator is a 2n plus 1. And then I subtract 1 to get 2n, and then I subtract 1, and then I subtract 1, and then I subtract 1, and voila. And a little bit of ding, ding, 2n factorial ends up being the denominator with a parentheses around that 2n. And notice that both sine and cosine have negative 1 to the n. They both have negative 1 to the n with their formula. And they both start with n equals 0. It's just if I start by doubling 0, I start with what happens when I plug in 0, which is the constant. If I start with plugging in 0 and I double and then add 1, I start with my exponent 1 term. I am going to be posting onto Google Classroom a formula sheet. Come on. And let me point out to you what that formula sheet has on it and how important these formulas are. This is looking at first the Maclaurin series where we're centered at 0. First few terms, be familiar with it. Sigma formula, know it. Then if my center is x equals a and I'm dealing with a Taylor series and not specifically a Maclaurin, then the first few terms look like that, and the formula, know it. Then we have e to the x, first few terms and formula, sine x and cosine x, first few terms and formula. Know every formula on this document well. Study it over the weekend. It is of extraordinary necessity. And if you start memorizing it this weekend, you're gonna just have this like in your soul, oozing out of your soul while you test. And that's always nice. So, what are we doing today besides finding out what cosine is? We are learning about how to algebraically manipulate from a known series instead of starting by scratch. And let me give you a little bit of a, okay, where did my stuff go? I know I pasted all you guys. There you are. Ha. Okay. So let me tell you what you don't want to have to do. Don't write down what I'm about to write down, but do write down the example. If you had to, from the Maclaurin series formula, come up with the series for the sine of x squared. I just want you to think about what you would have to do. You would have to look at what is the first derivative. And to do the first derivative, you go, oh, that's just easy. You go cosine, you go blah, derivative. And now take a look at the second derivative and start going, okay, I'm not real happy. Oh, that's a 2. Sorry, that is a 3x squared inside of the sine function. Yeah. If I have to take the second derivative, I have to now use a product rule while doing the chain rule. Are you starting to feel like I'd rather not? And that's only the second derivative. We still need the third derivative at minimum. So I want you to understand how much you don't want to do that if there is another way. And now let's look at the other way. I'm erasing. My computer is glitching like crazy, which is why I am taking it in to see the computer doctor this weekend. I'm going to have to, or this is only going to get worse. I'm using a different program because the other one was glitching that badly. So anyway, moving on. So here's what you're going to do. You can substitute into the variable of your power series any polynomial function. Substitute a polynomial into the variable of the known series. And what I'm going to do as I go through the examples is I'm going to first write out the function, the first few terms, and the sigma notation. Because you'll see the manipulation better if you first look at the first terms. As time goes on, you're going to find that you have a preference. Some people prefer to stick with manipulating one formula in sigma and let everybody come out of it. Other people need to get it faster if they're going through the first few terms. So I'm just going to do both of them. We already know that sine x, the first few terms are x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. The sigma formula is negative 1 to the n, x to the 2n plus 1 over parentheses 2n plus 1 factorial. So what I'm going to do is substitute into every single x the expression that I see in there. And I'm going to expect you to simplify, and I'm going to clarify to you what I expect with simplification. And when I substitute, I always substitute by first writing a parentheses so I don't mess up the algebra that should be going on. When you simplify the term by terms, I want your variable x to show up once. It is not directly multiplied by a number, and you see exactly what the exponent is. the 3x squared doesn't need to be simplified, but everybody else does.
Let me see if I can.
Okay, I'll give you a moment. This is why I missed that half hour. That half hour is the time for you guys to try something before I show it to you. Or to just finish a lesson. Ha! Okay, I'm going to keep going on this. And if you're ahead of me a little bit, try the sigma formula too and see if you can see how to simplify that so that you end up with its x not being directly multiplied by a number, and you can see exactly what its exponent formula is. So when I have multiplication under an exponent, because exponent is repeated multiplication, I can use a distributive property. I can distribute an exponent over multiplication, giving me 3 cubed times x squared cubed. And I'm doing this slowly to make sure that I clarify for you the rules you need to remember. Because that's one rule. The next rule you need to apply is when you have a base to a power, what do you do to the exponents? I should have my chat open. What do you do to the exponents? And that's why I'm going over this. One base. Yeah, and it happens to everyone, and that's why I'm doing this step by step. Or not everyone, but most. So the 3 cubed, I'm not going to expect you to go through that arithmetic, just like I don't expect you to go through the arithmetic of the factorials. But I want to make sure that you know all your exponent rules under extreme circumstances, which this is. So 2 times 3, 2 times 5. And once you've done it with a few terms, it makes it a lot easier to do sigma. So the sine of 3x squared, and I'm just going to write it here just to make sure it's clear. I am going to substitute into that x with a parentheses, 3x squared. The first thing I need to do is distribute the exponent over the multiplication. And then the next thing, you can leave the 3 to the n plus 1 power. You don't need to worry about simplifying that in any specific way. It's the variable that I want you to simplify. You need to see exactly what the formula is. When you multiply, be careful and make sure that you multiply with a parentheses around that addition. So we have the 3 to n plus 1 times x to the power of 2 times 2 and 2 times 1. And that's this piece, and then I'm just going to surround it with everything else. And if we had time, I would have us look at the graph of sine of 3x squared and the first few terms of this polynomial to see that they really do work. But you'll be doing that on your homework. All right, then, whoa. Next problem. Did you need me to show that other one for a moment longer? Okay. Then here is the next one. With this next one, you should see that you've got that 2x. That can be done by substituting a 2x into where the x's are located. But you also have multiplication by x. Order matters. So I'm going to recommend to you to first look at the function that you know the power series for. Think about what is your first step. What do I get with that first step without doing the power series? What is my second step? See what you get with the second step without going through the power series. Because there's nothing worse than going through a big giant power series manipulation, doing a couple of steps, and then realizing that your first step was the incorrect first step. Don't do that. Unpleasant. So I am going to do this the wrong way first so that you understand what I mean. Right now I'm going to go the wrong way. That's all right. The wrong way would be to see, oh, look at the multiplication. Yeah, okay. Look at the multiplication. I can start with e to the x and I can multiply, and I'm writing it in words. Well, I can multiply it by x. Yay. And then I can get this by substituting 2x into the x's. And then you go and you substitute it in, and then you realize, that's not the same thing as I was trying to get. But if you've already gone that far with sigma and you have actually done it with all of your terms, you might as well just divide by 2 and then you're good to go. But I ask you, do you really want to do 3 steps when you could do 2? No. So mapping out a proper ordering is valuable before you start manipulating the series. And I'm going to erase this, and we're going to start off on the correct foot. And that means we're going to first have, we're going to first have e to the x. And we are going to first substitute 2x into every x. You don't have to write down in words what you're doing. I'm doing that for the sake of teaching you. Then multiply by x. And then see that that's what you wanted to get. And as I go through examples, I'm going to be working both the term by term and the entire series. When you've practiced this enough, test problems are just going to be one or the other. You don't need to do both every single time. So let's see. I will use blue. The first few terms of e to the x, think about what they are. And then let's look at the sigma formula. Think about what that is. And this really is helping you. If you write these formulas over and over again, it's going to be very valuable. And now Let's manipulate that series. I have 1 plus, and I'm going to put a parentheses everywhere that I have an x. And now I'm going to substitute in. And when I say simplify, I want you to make it so that x is not directly multiplied to a number, and you can see exactly what the exponent is on the x. I can get my, there we go. So this piece, and I just realized I'm going to lasso. I love the lasso ability. I'm going to move that out. Really? Because I said lasso and you lassoed and then you didn't do what I asked. Okay, yes. And I want you to move, all of you. Fine, be that way, lasso. Don't lasso. I'll keep going. This is 2 squared x squared, 2 cubed x cubed, and you can simplify those coefficients, but right now I'm just going to keep moving on. In the sigma form, you need to distribute the exponent over multiplication so that you have 2 to the n times x to the n, and that would be considered simplified. And then next is multiply by x. I'll do this. And I do need to change color so that that is distinct. All right. I'm taking this and I'm multiplying by x. I'm going to go ahead and simplify. My 4 over 2 is a 2, and then I'm multiplying by x. I'm not going to simplify this constant, multiply by x. So that is approximately x times e to the 2x. Over here with sigma, I want you to take a moment to think, what did you actually do to each of these terms when you multiplied by x? What did you do to get them? And I'm going to over to the side say if you had started with x to the n and you multiplied by x, the exponent rule says add the exponents. You're adding 1. So you're just adding 1 to the exponent, and that's it. So if you know your exponent rules really, really well, you may want to actually manipulate the series and then let the terms pop out. Some people find that faster, but other people find that they'll make mistakes. Most important thing is to not make mistakes. So, yeah. And that is example number 2 done. If we had time, we would look at the graphs because they're so pretty and they really are the whole point of why we're doing this. But I'll complain once more today that we only have that we miss a half hour every single time we have class. All right, here we go. Take a look at the next one. And now let me point out to you that, let me see, where did I earlier write down? There we go. This star right here where I put, you can substitute a polynomial into the variable of the known series. You can also multiply a series by a polynomial, which we did in number 2. I will point out to you that it was kind enough, though, to be a one-term polynomial, if you catch my drift on that. A one-term polynomial. Every term in your polynomial has to distribute. And we'll be looking at more as time goes on. And now a third thing is you need to be able to add a polynomial to your power series. Those are 3 big things. So you need to be able to substitute, multiply, and divide comes with multiply, or add, and subtract comes with add. So you've got your 4 functions, your 4 operations, and substitution as well. Now I'm giving you a moment to see if you'll do it correctly. This is actually an important time for me to stop and ask you to try this on your own. See what you get with the first few terms. Be ahead of me a little bit. I'm going to write what cosine x is equal to. You start thinking about how are you going to create the series with this brought in. First few terms of cosine. Cosine starts with the constant, and it's positive when it starts, then it goes negative and sticks with the evens. Alternates back to positive, even. Alternate back to negative, even. And then the sigma is -1 to the n. I need to move this over. Don't worry about that yet. Okay. And then with cosine, it's x to the 2n, and that same 2n in a parentheses factorial. So have you had time to think about what you're going to do to create this Maclaurin series? Have you thought about it? I think people often take for granted that addition was the first thing they learned, so they assume that addition is going to be the easiest thing to do and make assumptions that they shouldn't make because they're not thinking about it, because they're assuming that it's going to be easy. I think you get what I mean by that. I usually have people write this down. I give it like a good 5 minutes so that the people who are going to make this mistake, which is probably half of you, learn from making that mistake. When you first start manipulating power series, you do the substitution and the multiplication, and they affect basically all of your terms. But when you're adding, what does it affect? It only affects its like term. And I've seen it time and time again. People will just kind of get into the mode of do this operation to everything. But when you're adding and you're doing polynomials, you are only able to add like terms. That's it. So if you're working with just the first few terms, then you're going to only change the one that is alike. So I'm doing 4 minus 1/2. If I can add this afternoon, that is 7/2. And then you just keep writing everybody else the way they are. But then comes the next question. How do you deal with the sigma notation? Anytime you have to do addition or subtraction of things in your power series, you're most likely going to be better off if you work with the first few terms, even if you're supposed to work with sigma. See what changes. And then when you go to sigma, keep in mind that adding only changes one term. Therefore, it's not going to change the formula. But I'm going to have to take some of these initial terms and pull them aside from sigma. Now, only this term changed, but I can't nicely write plug in 0, don't plug in 1, and then plug in 2. So you're going...
Could you write the 4x squared and then you say plus the sigma starting at 0? Does that work?
You can. It's just not simplified.
Okay.
And that's the big thing, is there are a lot of things that you can do, but it won't be in a simplified format. And when you're dealing with multiple choice, it won't be one of the answers. When you're dealing with free response, there's often a next step that you have to do after that.
Okay, so it's the in theory version.
Yes.
And then some extra work to simplify.
Yes. Yes, exactly. Mm-hmm. Yeah. If doing this is your final step and the directions don't say that you have to write a simplified version, then, you can just toss in front here a plus 4x squared. I recommend you throw it in front, not behind, because people accidentally think that that's part of the sigma formula, and it tends to be treated that way. But if you want to rewrite this where it's ready to deal with whatever operation comes next, then you're going to pull out the term that changes and any terms in front of it, even though they don't change. And then once the formula starts and will not be changing, that's going to start when n is 2. And then I can keep writing the formula. And it's important that you understand that when you do the addition, the general formula does not change. Everything else that we did changes the formula, but addition doesn't. All right, now that we've had that fun, we're gonna go into super fun mode. I set that problem aside in case you started thinking about it too hard. If I'm going to add not just a polynomial to my series, but an infinite polynomial with another infinite polynomial, you have to be careful. If you keep them in sigma form and try to add them together, you run into some issues that you might not realize need to be dealt with. because you've got to make sure that you're actually adding together who actually are like terms. And it's easy to mess that up when you're in formula mode. So I highly recommend when addition comes in to use the first few terms. So before I can do the addition, I'm going to have to find e to the negative x squared. To get e to the negative x squared, I'm going to start with e to the x, and I'm going to substitute into e to the x negative x squared. And you guys can write less things than I am writing. And I'm going to start with writing out several terms. E to the x starts with 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. When I plug in the negative x squared, that's okay. I've been having computer difficulties myself. Yay. I want to simplify this before I bring the cosine together with it. And I'm going to slowly make sure we don't mess this up. Negative sign is being squared. So I end up with positive, multiply the exponents 2 times 2, and then I am cubing a negative. That negative sticks around. I multiply my exponents. 2 times 3 gives me 6. And then my negative is to an even exponent, so it disappears. I multiply my exponents. 2 times 4 gives me 8. And I want to add cosine x to that. I am going to draw a line above this so that we don't mix things together. I now have that this is e to the negative x squared, and I want to add cosine x to it. So I'm going to write out the first several terms of cosine. Cosine is even. It is an even function symmetric to the y-axis. So it starts with the constant 1, and then it alternates the sign to a negative, and that term is x squared over 2 factorial. Then it goes back to positive, x to the 4th over 4 factorial. Negative, positive. And as I add my like terms together, I'm going to begin to see a formula that I can use for sigma if I had to write it in the sigma formation. But first of all, just adding the terms together. Most often, you're only asked to do the first several terms. You don't always do the general term. So here we go. 1 plus 1 is 2. Yay! Now, if I'm bringing two negatives together, how about I just go negative and then 1 plus 1/2. And then I'm having two positives with my x to the 4th. So I'm just going to put a plus. And then the coefficient is 1/2 plus 1 over 4 factorial. then minus, and then I have 1 over 3 factorial plus 1 over 6 factorial. And then plus 1 over 4 factorial plus 1 over 8 factorial. Now, if you needed to, you could simplify those coefficients. Those coefficients, though, are also helping you see the formula. So this is approximately what we get with e to the negative x squared plus cosine x. E to the negative x squared plus cosine x is equal to an infinite series. And then when I go to make the formula, I look at my last couple of terms. And I also keep in mind, what n am I on? The 2 comes from an n equals 0. The x squared comes from n equals 1. The x to the 4th from n equals 2, 3, 4. Do you think you have a formula? It's not the prettiest formula in the world, but it is a formula. We keep that negative 1 to the n because it starts with a positive and then alternates negative, positive, negative, positive. And my exponent is always doubling my n. My constant multiple, I can even have it in a parentheses out front, or I can just make it a big denominator. And actually, I might prefer to have it out front. I'm double checking my thoughts here. I am able to, if I wanted to, distribute this over here, but that is not one sum. That is two sums. So before I make an error, which I see myself really close to doing, I'm going to restart that. And I'm going to put it negative 1 to the n, x to the 2n, and then here put this massive formula for yuckiness. And that is 1 over 2n factorial. And then how do I get this? One over n factorial. I would really prefer not to have to do common denominator if I was not asked to. And so I would definitely avoid that. And voila. Isn't that fun? What time are we? I do not like Friday different schedules.
We get it at 12:45.
And we are currently, what do you know? I did it again. I finished early.